Okay, so again let us continue with our discussion on algebraic geometry. So let me recall the setup in which we are working. K is an algebraically closed field. For example, you can think of K to be complex numbers if that is convenient for you, and then the whole idea is you look at Kn with the Zariski topology on the one side, which is called as affine n space over K. Okay, and this is the rather this is the geometric side, and then on the other side you have the commutative algebraic side, and that is supposed to be the ring of functions on that space, and in this case of course it is a ring of polynomial functions on that space. So it is actually K of x1 through xn. So x1 through xn are n indeterminates, they are n variables, and if you think of this ring as a ring of functions on a affine space, because you give any polynomial, you take any polynomial, then you can think of it as a map from affine space to an to a1, which is just a1 is just k. Okay, so these are functions with values in k. Okay, and therefore this is the ring of polynomial functions, they are functions on the space. Okay, so the geometric side has got to do with the affine space, the commutative algebraic side has got to do with the functions. See, it is supposed to be a statement of Felix Klein, who said that the geometry of a space is supposed to be controlled by the functions on that you allow on the space, and this is, so geometry actually kind of comes into play when you have a space and you define what the functions on your space are going to be. Okay, so in this case the space is a affine space and the functions are the polynomial functions. Okay, and I told you that so of course just to recall what we have seen so far, the given any subset S here, you associate to S the common zero locus of S, which is the set of all points in affine space at which every polynomial in S vanishes. Okay, and then there is also a map that goes in this direction. Given a subset T of affine space, then you associate to T which is an ideal in the polynomial ring, and this ideal of T is just all those functions which vanish at every point of t, okay. And then this correspondence goes on the one side, the objects that are important here are the sub objects which correspond to ideals, and the objects that are important here are the so called algebraic sets, which are the closed sets, which has 0 sets of this form, okay. And of course you should remember that if I changed or if I replaced S with the ideal generated by S, you will still get the same 0 set, okay. So basically what you get is you get on this side, if you take the set of radical ideals, then you get a bijection with the set of all closed subsets, and this bijection is a it's an inclusion reversing correspondence, that which is quite obvious to see, because the larger the ideal is, the common zeros of all the functions in the ideal will grow smaller, okay. And the other important thing is that, so if you look at radical ideals you get closed subsets. On the other hand, if you look at maximal ideals, then you should remember, so maybe I think let me write this below, let me leave some space in between. So there are maximal ideals, so the maximal ideals are also radical ideals, because actually you should perhaps check as an exercise, probably you have already done it in a course in commutative algebra or algebra, that if an ideal is prime, then it is already radical, and since a maximal ideal is prime, a maximal ideal is also radical. But of course there are radical ideals which are not even prime, okay. But in any case, maximal ideals, the collection of maximal ideals is a subset of this, okay. And this, under this bijective correspondence, goes to the smallest possible closed subsets, which are actually the points. Of course when I say points, I'm thinking of a point here as a singleton subset of an, okay. So in other words, you can actually write an here, and of course the notation for this is the maximal spectrum of the ring of functions, okay. So max spec of a ring, commutative ring with 1 means the collection, the set of all maximal ideals in the commutative ring. So what you must understand is a point here is a maximal ideal of the ring, okay. And the fact is that given a maximal ideal you get a point, and conversely, okay. So in particular, for example, if you take a maximal ideal of the maximal ideal will always look in this form. It will be generated by xi minus lambda I for a tuple for an n tuple lambda 1 etc lambda n, which will be a point of an, and this is the correspondence, because the 0 set of this is this and the ideal of this will be that, okay. So you should remember that in this direction the map is taking the ideal, it is the I map, and in this direction the map is the Z map, which associates the 0 set, the common 0 locus, okay. And in fact I told you that this also uses the Nullstellar ansatz, okay. In a way it's an avatar of the Nullstellar ansatz, probably weaker or stronger, probably weaker, but let us look at that in the exercises, but the point is this is a non-trivial statement. Okay, what is trivial is if you give me an ideal like this, it is maximal is reasonably trivial to check, but to conversely say that every maximal ideal is of this form, which is true only when K is algebraically closed, or at least when K is algebraically closed, that is non-trivial. Okay, and that uses Hilbert's Nussbaum-Satz. So the what lies in between are the prime ideals. The prime ideals, the collection of prime ideals, they correspond to what is called the spectrum of the commutative ring, and you see the spectrum of the commutative ring is supposed to be the set of all of its prime ideals, and therefore you think of a prime ideal here as a point in the spectrum. So a point here is a maximal ideal and a point here is a prime ideal. Okay, and of course this is contained, as I told you, prime ideals are radical, maximal ideals are prime. Okay, and what happens is that so what corresponds to prime ideals on this side are what are called as affine varieties in AN. So by this I mean the definition is these are all algebraic sets, these are all closed sets which are irreducible. Okay, so prime ideals correspond to irreducible subsets which are closed. Okay, and that is a theorem I stated in the previous lecture, and I just stopped with that because the last lecture actually stopped with the definition of what an affine variety is. Okay, an affine variety is an irreducible closed subset of affine space. Okay, and why are they important? They are important because we will see later that any variety, that any closed subset can be broken down into a finite union of affine varieties, and the decomposition is unique if you make sure that there are no redundancies, that is no affine variety in this is contained in, no affine variety in the decomposition is contained in some other affine variety in the decomposition. So every closed subset can be broken down into a finitely many affine varieties only in a unique way, essentially a unique way. I say essentially because you can always you can always permute the pieces in the union, but that should not affect the union or the decomposition. And so that is one important thing about affine varieties, because they are like building blocks of algebraic sets. Every algebraic set is broken down into union of affine varieties, and this is very, very important because later on, for example, I told you probably in the first lecture that there is a more advanced or I should say sophisticated language of algebraic geometry which involves what are called as schemes, and schemes are some spaces with functions, okay, with rings of functions, and in fact what you have is not just rings of functions, you have sheaves of rings, which means that you have rings of functions on every open subset of the space. So it's data not only with the space with a ring of functions on the whole space, but it also comes with, for every open set in this space you will have a ring of functions. So your this whole data is called a sheaf of rings, and a scheme is something to like that, which consists of space and a sheaf of rings, okay, where the sheaf is a collection of rings for every open set in the space. But the important point is, the technical point is, a scheme is supposed to be locally modeled in this way. It is supposed to be made of affine pieces. So for all of algebraic geometry, no matter how general algebraic geometry you do, these affine pieces, these are the building blocks, these are the building blocks, and that is the reason why these have to be first studied. Okay, so you should understand that affine varieties are important because they are the building blocks even in the most sophisticated form of the theory. Okay, and the other important thing is that the other important thing is of course that these sets are topologically irreducible. Okay, and you know irreducibility I have told you is a very strong form of connectivity. So they will have nice properties with respect to maps. So for example in topology you learn that the image of a connected set under a continuous map is again connected. Okay, so if you have a topological space and you have a map, a continuous map from the topological space into another topological space, then the image of a connected set if in the source topological space will be a subset of the target topological space which will be connected. Okay, and the same thing will happen for irreducible subsets. Okay, so irreducibility is a very nice thing to have on a subset. Okay, so now let me try to prove this part. So let me recall definition. So this I am just recalling. A topological space, a subset Y of a topological space. So I am just abbreviating topological space to TOP SP. X is called irreducible if Y cannot be written as Y1 union Y2 with Y1 Y2 non-empty proper closed subsets. Okay, if a topological space can be written as Y1 union Y2 where Y1 and Y2 are non-empty proper closed subsets, then we say that the topological space is reducible. Okay, and the definition of irreducible is that it should not be reducible. Okay, and what happens in the case of varieties, as we will see, what happens in the case of algebraic sets here, namely closed subsets of affine space, you will see that you will get it, you will be able to break it down into not just a union of two, you will be able to break it down into a union of finitely many subsets which are themselves irreducible. Okay, and they will be called the irreducible components. Okay, but and that will be called the reducible decomposition of your given closed set. Okay, so that is where we are heading to. Fine. So of course this definition, as I told you, implies that if Y is irreducible, then it is connected. Okay, because connected is for it to be connected you should not be able to write it as a disjoint union of proper closed subsets, non-empty closed subsets. Okay, and that is certainly not possible if you can't even write it as a union of non-empty proper closed subsets. Okay, so irreducibility is a very strong form of connectedness. I told you that irreducibility has lots of nice properties. One thing that comes is that if space is irreducible, then if a subset is irreducible, then its closure is also irreducible. So its irreducibility is not going to be affected if you add the boundary, which is what you do when you take the closure of a set. And this is also true for connectedness. If a set is connected, then its closure is also connected. And then but the other more important thing is that you see the more important thing about an irreducible space is that every non-empty open subset is dense and is itself irreducible. That is another very important property, okay, which I hope you would have tried as an exercise, otherwise you should try it. It's a pretty easy exercise. So what it tells you is that if you take an irreducible space and take a non-empty subset, then you can test on that subset all those properties which will be preserved when you take a closure, okay. That subset will because the closure of that subset will be the whole space, and that's so you can test on any non-empty open subset, and any non-empty open subset will be dense. And that also tells you that if you take any two non-empty open subsets, they will intersect, okay, they cannot be disjoint from each other. So these are the nice properties of irreducibility, and later on it will come, we will again look at it. Probably it's not so hard, you can even check it offhand. I think that the image of an irreducible set continues to be irreducible under a continuous map, okay, which is the same kind of statement that you get for a connected set, okay. Now I go to this theorem which I stated last time. So the theorem is the following: if I in the polynomial ring in n variables over k is an ideal, then Z of I, the 0 set of I, namely the points in an which are common zeros of all the polynomials in I, is irreducible. This is a subset of this topological space. You see this topological space is just Kn given the Zariski topology, okay. So since it's a subset of a topological space, this definition applies, and you can put the condition that this subset is irreducible, and the theorem says that this is irreducible if and only if the radical of I is a prime ideal. So what this means is that if I already started with the radical ideal, I mean if I already started with the prime ideal, then Z of I will be irreducible, and conversely if I already started with the radical ideal, then saying Z of I is irreducible is the same as saying that the ideal itself is prime, okay, and that's essentially what gives you this this correspondence in the middle, okay, that the affine varieties in An, they correspond to prime ideals, okay. So well, so the proof is quite straightforward. So let's do both ways. So let's begin with let's assume a radical of I is prime. Suppose radical of I is prime. What do I have to prove? I have to prove Z of I is irreducible. To show Z of I is irreducible, okay, but actually you see Z of I is the same as Z of rad I, okay. This is something that I told you last time. Two ideals J1 and J2 have the same set of common zeros if and only if the radical of J1 is equal to the radical of J2. So it's since I and rad I have the same radical, namely which is rad I, they both have the same zero set, okay, but even otherwise this is quite trivial to see directly, okay, because rad I, mind you, is defined to be all those polynomials some positive integral power of which lies in I. So it's like taking the radical of an ideal is like expanding that ideal to include nth roots of its members, positive nth roots of its members, okay. That is nth roots for positive n, right, and so anyway, so how do I check a set is irreducible? So the logic is I have to check that it's not reducible. I have to check that it's not reducible. So I have to check that if it can be written in this form with y1 and y2 as closed subsets, and if I assume that y1 and y2 are both non-empty and also that y1 and y2 are both proper, that should not happen. That is what I have to check. So what I will do is I will assume that it can be written as in this form with y1 and y2 non-empty, but I will assume further that y1 is proper closed subset, and I will try to prove that y2 is not proper, namely that y2 is everything. If I do that, then I am done. Okay, so that proves that it is not reducible, in other words that it is irreducible. So what I will do is suppose that z of I is y1 union y2 where y1 y2 are non-empty closed closed subsets. So here I have to go back to the definition and stress on something which I haven't written there. With y1 comma y2 non-empty proper closed subsets, mind you, of y. Okay, that's something that I hadn't written, but I did say that in my last lecture. So let me stress it. When I say so I told you y is just a subset of a topological space. What is the meaning of saying that a subset of y is closed in y, that you have a closed subset of y? This is the language of induced topology. A subset of y is said to be closed subset of y if it is gotten by intersecting y with a closed subset of the ambient space, the larger space x in which y sits. Okay, so when I write z of I is y1 union y2 where y1 y2 are non-empty closed subsets of z of I, what you must understand is that since z of I is already closed in x, it follows that y1 y2 are not just closed subsets of z of I, but they are actually closed subsets of x itself, because a closed subset of a closed subset will continue to be a closed subset. Okay, see, in other words, when I say y1 is a closed subset of z of I, it means y1 is z of I intersected with a closed subset of x. Okay, but then you see z of I itself is closed in x, and so if I intersect with another closed subset of x, the intersection of finitely many closed subsets is again a closed subset in the topology, because the axiom of topology, for axioms for a topology, if you take the axioms for closed sets, tells you that you take any finite number of closed sets and you take the intersection, the result is again a closed set in the whole space. So what this tells you is that y1, which is supposed to be the intersection of z of I with a closed subset of x, is itself a closed subset of x. So let me stress that suppose z of I is y1 union y2 where y1 y2 are non-empty closed subsets of z of I with y1 a proper subset of z of I. Of course I will then try to prove that y2 is equal to z of I, that in other words that y2 is not proper. Okay, then note that y1 y2 are closed in the larger space x, which is actually in our case an, because by definition, as I just told you, y1 has to be z of I intersection with a closed subset of an, but z of I is already closed in an, and the intersection of two closed subsets of a topological space is again a closed subset. So the reason is, since z of I is already closed, it's already closed in an by definition, because that's how the Zariski topology was defined. The Zariski topology was defined just by taking for the closed sets subsets of the form z of I. Okay, so but what does that mean? saying that y1 y2 are closed in an means that y1 and y2 are the 0 sets of some ideals, okay. So this implies, so y1 is z of I1, y2 is z of I2 for I1 I2 ideals in k x1 etc etc, okay. This is what you get. But then what is now y1 union, so if you take z of rad I, which is z of I, which is y1 union y2, is actually z of I1 union z of I2, okay. And you know, but this is the same as z of I1 I2, this is the same as z of I1 I2, because this is something that we this is how we proved that sets of the form z of I they form a topology by declaring such sets as such subsets as closed subsets. In fact, what we proved is if you took z of S1 union z of S2 union etc up to z of Sm, where SI's are subsets not even ideals, then the union is just z of the product S1 times S2 times etc Sm. We proved that, okay. So this is z of I1 I2, okay. And you see it's at this point that you know, I'll use so I'll now use the Nullstellan sets, okay. So what will happen is, you see, apply I, if you apply I, the Nullstellan sets tells you that since I of z of j is rad j, okay, mind you this is a statement that involves the Nullstellan sets, and that is valid for any ideal j. Actually I of z of j always contains rad j, that is very easy to see. The non-trivial thing is to say that I of z of j is contained in rad j, namely it is a statement that if a polynomial is an I of z of j, namely if a polynomial vanishes on z of j, then some power of the polynomial is in j. You cannot have a polynomial some power of which is not in j to vanish on all the zeros of j, that cannot happen, okay. So this statement uses Nullstellan sets, and if I apply this on both sides, what I will get is I will get radical of rad I is equal to radical of I1 I2, okay. I just want to say that this contains I1 I2, okay. This is the way I have to go, okay. So you see radical of an ideal always contains the ideal, okay, because the radical is supposed to be all those elements some positive power of which is in the ideal, and the first positive power of every element of the ideal is in the ideal, so the ideal itself is contained in its radical always. And see the fact is that this is rad I, okay, because taking rad more than once is not going to change anything, and this is prime, this is prime. So what you are getting is you are getting a prime ideal contains the product of ideals. Now you see we use this following fact from commutative algebra. It is a very simple fact that if a prime ideal contains a finite product of ideals, then it has to contain at least one of them, okay. So here is a lemma, a very simple lemma from commutative algebra. If a prime ideal contains a finite product of ideals, then it has to contain at least one of those ideals, one of the ideals in the product. Of course, you know, of course all this is in this statement the background I am assuming is that you are working in a commutative ring with one and you are having finitely many ideals, and if you have finitely many ideals j1 j2 through jm, then their product is j1 dot j2 dot etc jm, which consists of just finite sums of products of m tuples taken from the Cartesian product of all the j's, okay. And if a prime ideal contains the product j1 j2 jm, then it has to contain some ji, and this is just this is very easy to see because it is just definition of prime ideal, that if a prime ideal contains a product, then it has to contain one of the finite product, then it has to contain one of the factors of the product. It is just a restatement of that if you try to work it out. So what this lemma will tell you is that rad I has to contain I1 or rad I has to contain I2, but then this now you apply Z, okay, you apply Z and to take the 0 locus, and remember that when you apply Z the inclusion is reversed. So what you will get is Z of rad I is contained in Z of I1 or Z of rad of I is contained in Z of I2. This is what you will get, and mind you, but Z of rad of I is, mind you, is just same as Z of I, and Z of I1 is Y1 and Z of rad of I again is Z of I here, and this is Y2. So what you are saying is Z of I is contained in Y1 or Z of I is contained in Y2, okay. But what we have already what we started with was that Y1 and Y2 are contained in Z of I. So what this means is that either Z of I is equal to Y1 or Z of I is equal to Y2, but then you are assuming that Z of I is not equal to Y1. So what this will tell you is that Z of I has to be equal to Y2, and that tells you that you cannot reduce Z of I, and okay. So let me write that down. This implies that Z of I is equal to Y1 or Z of I is equal to Y2, which implies that Z of I is equal to Y2, since Z of I is supposed to properly contain proper subset of supposed to properly contain Y1, okay, and this implies that Z of I is irreducible, okay. So we have started with rad I prime, okay, and we are able to deduce that Z of I is irreducible. Now we will do the other way, we will assume Z of I is irreducible and show that rad I is prime, okay. So conversely assume that Z of I is irreducible, assume that Z of I is reducible, we will show rad I is prime, okay. So how do you, so this is again translation. You just have to check the condition for a prime ideal. You have to take a product. How do you check something is a prime ideal? How do you check an ideal is a prime ideal? You take a product of two elements of the ring as belonging to the prime ideal and demonstrate that one of the two factors of the product is that ideal, okay. And so what we will do is, so let f times g belong to rad I, let the product be in rad I, okay. So what this will tell you, this will tell you that the ideal generated by f into g is a subset of rad I, okay, because if an element belongs to an ideal, then the ideal generated by that element is also in that ideal, because the ideal generated by an element is just simply multiples of that element by ring elements, okay. So if I now you apply Z, if you apply Z, I will get Z of fg contains Z of rad I, and but you know Z of fg is just Z of f union Z of g. Okay, this is exactly the same statement that Z of I1 union Z of I2 is Z of I1 I2. Okay, so Z of fg is Z of f union Z of g. Okay, and of course when I write Z of f for a single element f, by that I mean Z of a single element f is the same as Z of the subset consisting of the single element f, and which is also the same as Z of the ideal generated by f. They are all one and the same. Okay, so what happens is that, so you know, so now you can, so what this tells you is that, you see, Z of rad has been written as ZF intersection Z of rad union Zg intersection Z of rad. Okay, you see Z of f is a closed ZF, this union contains this, so you intersect this with the smaller subset, you will get back the smaller subset. So if I intersect this with Z of rad I should get Z of rad and that's, and intersection, you as you know, distributes over the union by simple set theory. Okay, so you get this, but what you must realize is that this is, if I call this as y1 and if I call this as y2, what you will notice is that y1 is a closed set. It is a closed set because it is the intersection of two closed sets, so it is a closed set. Similarly y2 is a closed set, and you have written Z of rad I as a union of two closed sets, but mind you Z of rad I is the same as Z of I, but what is the assumption on Z of I? The assumption on Z of I is that it is irreducible. So the moral of the story is that either one of these is empty, okay, and if both are non-empty, then one of them has to be the whole Zi itself. Okay, so let's write that out. Let me write that out here. Since Z of I equal to Z of rad I is irreducible, we have and y1 y2 are closed, we have the following possibilities. So I want to say y1 is non-empty, y2 is non-empty. Okay, so let's write down y1 is, if y1 is empty, this will tell you that that means you, so that will imply that Z of f intersection Z of rad I is empty. Well, this intersection is supposed to be Z of f union Z of the ideal generated by f union rad I. Right, this is what it is supposed to be by definition, because what is how do you show that the closed sets form a topology? How do you show algebraic sets form a topology? So what you if you recall, you can recall that Z of if you take intersection over alpha or lambda in capital lambda, some indexing set of Z of S lambda, this is just Z of the ideal generated by the union of S lambdas. Okay, if S lambdas are subsets of the polynomial ring, okay, and you take the Z S lambdas, these are a collection of closed sets. How do you show that the intersection of, see, how do you show that the intersection of an arbitrary collection of closed sets is closed? it follows from this calculation, okay. So z of f intersection z of radii will be z of f union radii, ideal generated by f union radii. And so what that will imply is, if I apply I to both sides, if you apply by I to both sides and use this z of I of z of j is rad j. So what I will get is, if I apply I to both sides, you will get radical of the ideal generated by f union radii will be, if I apply I to the null set, okay, then I will get the whole ring, okay, because what is I of a subset? It is all those polynomials which vanish on the subset, okay. I of a subset of affine space is all those polynomials in the polynomial ring which vanish on that subset. But if that subset is empty, there is nothing to test, every polynomial will satisfy this condition, therefore I of null set will be just the whole polynomial ring, okay. And you know, if this happens, I mean I essentially have to show that if this happens I am done, otherwise I have to proceed further, okay. So what does this mean? This means that f the ideal generated by f union radii is itself the polynomial ring. See, so this is again a fact I am using, that you know, if an ideal if the radical of an ideal contains a unit, then the ideal itself contains a unit, because saying that the radical of an ideal contains a unit, say 1, tells you that there is some power of this which is equal to 1, there is some power of this, the ideal generated by this union, which is equal to 1, but then if the some power of an element is equal to 1, then that element itself is a unit, okay. That means that the ideal generated by this itself is the whole polynomial ring, okay. And what this will tell you is that so you know, there is some so what this will tell you is the following, that so there exists G1 etc. Gm in radii such that sigma fg plus sigma over I equal to 1 to m fi gi is 1. This is what it tells you, okay. I mean, an element in the ideal generated by the union like this will look like this. You will have to pick you have to pick finitely many elements from this subset and then take ring linear combinations of that, and such a ring linear combination is equal to 1 because 1 is there on the right side. And now what I want to say is that from this we will have to say that so you know, if this happens, that is if y1 is empty, it should more or less follow that if y1 is, say that again, yes, if y1 is empty, yes,
radii is equal to z of g intersection z of radii.
Z of
left hand side is equal to the remaining thing on z of
oh,
radii is y2.
Z of, oh I see, you will just get z of radii is equal to z of I g intersection z of radii, and then you will get, therefore
you will get z of radii contained in z of g.
Okay.
So if you apply I on both sides,
you will get g belongs to radii, right? You will get g belongs to radii. Okay, okay, okay. So probably so this is not required. You are right. Okay. So let me get rid of this. Good. Let me get back to the easier part of the argument, but I would strongly encourage you to think about that, whatever I wrote down. Okay. So and the fact is that also will lead to something. Okay. That will also lead to what you want, but you have to. So the point is you have to keep translating back to the geometric side. if you are on the geometric side you should translate to the ideal side, if you are on the ideal side you should translate to the geometric side by applying this I and Z appropriately. Okay, so as one of you has rightly pointed out, what you should do, what one does is that if y1 is empty, then I mean z of, it's obvious that z of radii is just z of G intersection z of radii, and so which means that z of radii is contained in set of G, right, and because the right side is contained in set of G, and now you apply I, you will get I of z of radii, which is just rad of radii, which is radii containing I of z of G will be just radical of the ideal generated by G, okay, and to which G belongs. Okay, so if y1 is empty, you get G is in radii. Okay, all right. So you assume y1 is not empty. Okay, if y2, similarly if y2 is empty, then you will get F in radii. Mind you, F times G is in radii, so you have to prove either F is in radii or you have to prove G is in radii. Okay, and y1 equal to empty directly gives you G is in radii. Similarly, y2 is empty implies F is in radii, okay, and you are done. So assume both are not true. Okay, so assume both y1 and y2 are non-empty. Okay, so you will have to thrash out all the possibilities. Okay, suppose y1 is proper, then irreducibility of, you're right, z of radii implies that if this is proper, then that cannot be proper. If y1 is proper, then y2 cannot be proper, so y2 has to be everything. Okay, and in that case you see G belongs to radii, right. So you are done essentially. So let me write that down. Suppose y1 is proper, then irreducibility of z of radii implies that z of radii is y2. Okay, and this implies that again the same argument, literally z of radii is equal to z of G intersection z of radii, and this will imply that G, I guess this will imply G is in radii. Okay, so if y1 is proper, you will get G is in radii. Similarly, if y2 is proper, okay, you will get F is in radii. Okay, similarly y2 proper will imply F is in radii, and that completes the proof. Okay, right. So it's very clear that an ideal here is prime if and only if the radical of an ideal here is prime if and only if the corresponding zero locus here is irreducible. Okay, that proves it. Okay, so I'll stop here and then we'll continue in the next part with some examples. Okay.